record this. So we're working on section 5.5. We started that last class, and we are going to finish it today. It finishes all the material that is on the next test. And at the end of class, I'll talk about the next test as well. I put up a review sheet for it. And so the next test is not this Wednesday, but next Wednesday, the 24th. So that is when the next test is. And then just a reminder, I kind of said this real quick last class, but this coming Wednesday, the 17th, we will not have class. I have an appointment that I cannot change. It's been made for months. So, but it gives you time. It's kind of a nice time for this to happen because it gives you time to actually then work on the review sheet. And I already have the review sheet up on Canvas, and I'll show you all of that before we end here today. And so you should try the review sheet so that then next Monday I can answer any questions you have about the review sheet and all that stuff. And then next Wednesday will be that test. And then the following week is spring break. So you kind of get a nice little break from math during spring break. So does anybody have any questions before I finish section 5.5 today? No. Okay. Yeah, so I'm going to show you on the review sheet too, at the end of class, that the identities is not like the biggest part of the test. So the biggest part of the test is actually this section solving equation, section 5.5. And then after that, the next biggest part on the test is the inverse, finding using inverse trig functions. So the identities part is actually not that big of a part of the test. And I'll show you guys that. So you probably don't have to worry quite as much about the identities. Okay. So then this is section 5.5 continued. Because we started it last class. So last class we were just solving equations. We're going to do the same thing today, but we're going to look at some special solving techniques. So some techniques that'll help us out to solve some equations when they're hard to solve. So some special techniques for solving trig equations. All of the problems we're going to do here, we're going to solve in that interval from 0 to 2 pi. So, solve in the interval interesting. Okay, I can fix, I'll look at that. Like if you click on our class, it doesn't take you here. You have to actually put in the, let me make sure that's not somebody else saying they can't get into class. That dinging noise on the computer here. No. Okay, I'll investigate that after class. So, but I'm assuming you could obviously still got in. So the meeting number and password works. Okay, yeah, I'll work on the other part. Okay, thanks for letting me know. So, solving in the interval. So I want to solve in the interval from 0 to 2 pi. All of these techniques that we're going to do, they work even if you are just finding all solutions. So they're not specific to solving in the interval from 0 to 2 pi. That's just where we're going to solve these equations. So the first technique is sometimes you have to factor. Okay? So for example, if I was trying to solve the sine squared of x minus 3 sine x plus 2 equals 0, right? So like last class when we were doing problems, the first thing we would do is we would isolate the trig function, right? So I would just get the sine x by itself, or I would get the cosine x by itself. The problem here is that I cannot isolate the trig function because I have a squared function here and I have it just to the first power. So I'm not able to isolate it. Instead, what we want to do is, it kind of looks like a quadratic equation, except it's not x's or y's or z's, it's sines. So you can think of this is kind of like the equation z squared minus 3z plus 2 equals 0, right? Where basically all I'm saying is let z be equal to sine x. So now it looks like a quadratic equation. So what could I do to, how could I factor that equation? Yeah, z minus 2 times z minus 1. So z minus 2 equals, oops, not equals, times z minus 1 equals 0. Okay, so really our z, as I said, is sine x. So this is really just saying sine x minus 2 times sine x minus 1 equals 0, right? Do you have to do the pink part if you can see going from this first line here to this second black line? No. But the pink part, the reason why I wrote the pink part is because sometimes it's hard for people to see how to factor the equation when you have all the signs in there. So if that's the case for you, then I recommend kind of finding this, like I call it like a dummy variable. So it's like a variable z. You could pick whatever letter you want, right? You could have used h or k or whatever letter you want. And then think about it that way and then factor it. And then you can go back to the signs. So now it's kind of similar to problems we did last class, right? So I have two things that are multiplied together that give me 0. So that means either the first one has to give me 0. So either sine x minus 2 has to be 0, or the second one, sine x minus 1, has to be 0. And then I'm going to solve each of those equations. So in this first one, I'm going to add 2 to both sides. So we're looking for where the sine of x is equal to 2. So what do you think? Is the sine of x ever equal to 2? No. So remember the sine function, right, looks like this. And it always bounces between 1 at the top and minus 1 at the bottom. So the sine is never going to be equal to 2. So this part here doesn't give us any solutions. So now we'll look at the other side. So I'm going to add 1 to both sides. So we end up with the sine of x being equal to 1. And between 0 and 2 pi, when is the sine of x equal to 1? Yep, pi over 2. So when x is equal to pi over 2. And so our only solution here just ends up being x equals pi over 2. We only get one solution here, right? So if I'd gotten solutions on both pieces, then I would have taken the answers for both pieces like we did last class. But here I don't have any solutions on that first piece. So all of my solutions are coming from that second piece. Questions? No. yeah, it's not too bad. So one of the things you could do is factor. We're going to practice more factoring too in a couple other problems here. But before we do that, we're going to do some other stuff. Is everybody okay if I move on to the next page? Does anybody need me to wait? Okay. So the second thing you could end up having to do is you could end up having to use an identity. So I have two examples of this one here. So for instance, I have sine x equals minus cosine squared x minus 1. And so part of the problem here is if you're given a problem and your problem has different trig functions in it, so you're trying to solve it, but they're not all sines or they're not all cosines, then we run into a problem because I can't do the factoring trick we did on the last one because everything's not a sine or a cosine. So the first thing, since I have a squared function, I'm still just going to pull everything over to the left-hand side. So if I move everything over, we really have cosine squared x plus that sine x minus 1 equals 0. So I've basically just taken the cosine squared x, moved it to the left-hand side, taken the minus 1, moved it to the left-hand side. And the idea is I would like to either change everything to cosines or change everything to sines. Now, oh yeah, it is plus 1. Thank you. So what I can do is if I'm trying to change everything to cosines or everything to sines, generally if you have something squared, we're going to be trying to use the Pythagorean identity. So remember, and this is off of that sheet, the Pythagorean identity says that the sine squared of theta plus the cosine squared of theta equals 1. So I could rearrange this to be cosine squared theta is the same as 1 minus sine squared theta. Does that make sense? Okay, so I'm going to replace my cosine squared x with 1 minus sine squared x. So this part here becomes 1 minus sine squared x. Then I still have this plus sine x plus 1 equals 0. And if I combine the like terms, I really have minus sine squared x plus sine x plus 2 equals 0. And now I'm back in the same situation I was in before where I'm trying to factor this polynomial, right? So if you think about this, this is really like I'm trying to factor minus z squared plus z plus 2 equals 0. So anybody know how minus z squared plus z plus 2 equals 0 would factor? You know, it's a little weird because the minus is there, right? In front of the z squared. So remember, you could move everything to the other side to factor it, right? So 0 would also be equal to z squared minus z minus 2. So how would I factor that? You know, you guys probably were all like, oh, we're not going to have to factor in trig, right? So somebody suggested z minus 1 times z minus 1. So z minus 1 or z and a 1 are definitely part of it, but z minus 1 times z minus 1 would wouldn't work out. Z minus 2 times Z plus 1 does work. So 0 is going to be Z minus 2 times Z plus 1. You could write it as Z plus 1 times Z minus 2. That works as well. So really, right, we're solving 0. Remember, our Z is a sine, so 0 is equal to sine x minus 2 times sine x plus 1. And then just like before, I have to set each of those pieces equal to 0. So sine x minus 2 equals 0, sine x plus 1 equals 0. And then we'll solve each one. So sine x equals positive 2. So it happened to give us the same thing as before, right, on this piece. So again, this piece, no solutions. On this side, we're going to have sine x equals negative 1. So when is the sine of x equal to negative 1? Yeah, 3 pi over 2. So the only answer we get here is x equals 3 pi over 2. Sometimes people try to put into ALEKS or try to write down on a test like x equals no solution and 3 pi over 2. It's not that x equals no solution. It's just that one part gave us no solutions, right? But all together, we do have a solution. It is 3 pi over 2. So if there is a solution, you put 3 pi over 2. The only time you should be writing or selecting no solution on ALEKS is if both pieces didn't give us an answer. Questions? No. We're going to do another one that uses an identity, just so you can kind of see some different ways of using identities. So, does anybody need me to wait to go on to the next page? No? Okay. So, example 2, minus sine x plus cosine of 2x equals 1. So again, I have sines, I have cosines, one has an x, one has a 2x, so nothing's really matching up. So if you remember, we do have identities for the cosine of 2x. If you go to the identity sheet, right, and you look at the double angle identities, there's actually 3 different ones for the cosine of 2x. So the cosine of 2 theta, these are the 3 that show up on the sheet. So cosine theta squared minus sine squared theta. The cosine of 2 theta is 1 minus 2 sine squared theta. And the cosine of 2 theta is 2 cosine squared theta minus 1. So in this case, I actually have 3 to choose from. And so the idea is like, well, which one should I choose? And so if you look at our problem has a sine in it. We're going to be replacing this part with one of these identities. So I want to get it into all sine values. I don't want any more cosines. So since I already have a sine here, I would like to get everything into sine values, which means I should use this middle one here. Right? This middle one will take my cosine of 2 theta and turn it into 1 minus 2 sine squared theta. So the only trig function that will be left will be sines. So that's what I'm going to do. So we've got minus sine x plus this part here becomes 1 minus 2 sine squared x equals 1. So I just replaced it. And then the next thing I want to do is we're going to want to factor this, so we're going to want to move everything to one side. So I've got minus sine x plus 1 minus 2 sine squared x. And then if I move that 1 over to the other side, it's going to become minus 1 being equal to 0. So questions on anything that I have done so far? No. You guys are pretty questionless today. Okay. So now the 1 and the minus 1 would cancel each other out, right? So that cancels with that. And now I am left with minus sine x minus 2 sine squared x equals 0. And I think we kind of did something like this the other day, where I could factor a sine out, right? So all the pieces that I have left all have a sine in them. So I could factor the sine out. So sine x times negative 1 minus 2, and I'm left with a sine x equals 0. Questions? You could factor out the negative. Sure, it doesn't matter. Would you guys like it if I take the negative out too? So you could have factored it to be minus sine x times 1 plus 2 sine x equals 0. Yep, that's totally fine. You could have. So I didn't at first. In the end, it's going to turn out exactly the same whether I factored it out or I didn't factor it out. So you can or you can't. It doesn't matter. So now I have two pieces. I'm going to set each piece equal to 0. So minus sine x equals 0. And 1 plus 2 sine x equals 0. The minus sine x being equal to 0, you can think about if I divide both sides by negative 1. This is saying sine x is just equal to 0. Remember, we're solving on the interval from 0 to 2 pi. So when is the sine of x equal to 0 between 0 and 2 pi? Yeah, 0 and pi. Then we'll go to the other side. So 2 sine x equals negative 1. Divide both sides by 2. So we're looking for when is the sine of x equal to minus 1/2. So when does that happen? Yep. So one of the times is 7 pi over 6, and when else? Yep, 11 pi over 6. So in this case, I get 4 answers, right? So my final answer is going to be x equals 0, pi, 7 pi over 6, and 11 pi over 6. So all 4 of those are answers. Questions? No. Okay. I don't know if I said it at the beginning, but there were 3 kind of different techniques we could use. So one was to factor. So we did that, and we've done that in other problems too. The second one is sometimes I needed to use an identity. So we've done that. The third one is that sometimes I need to actually square both sides of my equation. Does anybody need me to wait to go on to the next page? Okay, sure. Yeah, let me know when you're ready. Okay. All right, so third one is to square both sides. So, example 1, square root of 1 minus cosine x equals sine x. So here's one where we're going to square both sides. And part of the reason we're going to square both sides is because it has a square root in it, right? So usually when we have a problem that has a square root in it and we're trying to solve it, we often square both sides. So if I square the left-hand side, 1 minus cosine x, quantity squared, equals sine x squared. So if I take that left-hand side, square root of 1 minus cosine x squared, it's just going to give me 1 minus cosine x. And if I do the right side, it's going to give me sine squared of x. And so now I'm kind of pretty similar to the problem we did before, right? I have cosines and I have sines. But I would like to get everything into one of the variables. So I usually try to get rid of the squared variable. So just like before we used the Pythagorean identity, that sine squared theta plus cosine squared theta equals 1. We're going to use that same identity. So sine squared theta is going to be 1 minus cosine squared theta. I see. All right. Also, so 1 minus cosine x, and sine squared is 1 minus cosine squared x. So if I move everything over to the left-hand side, I'm going to have 1 minus cosine x minus 1 plus cosine squared x equals 0. And the ones would cancel, right? And so I'm left with cosine squared x minus cosine x equals 0. So just like before, we're going to factor out a cosine. So cosine x times cosine x minus 1. And I've got two pieces, and I'm just going to set each piece equal to 0. So the cosine of x is equal to 0, or the cosine of x minus 1 equals 0. So cosine x equals 0. When is the cosine equal to 0? Between 0 and 2 pi. Okay, pi over 2 and 3 pi over 2. And this one is giving me cosine x equals 1. So x is going to be equal to what? Yep, so the cosine of x is equal to 1 at 0. So my answers here are pi over 2, 3 pi over 2, well, I should be a little careful, and 0. So these are my potential answers. All right, so all the other problems, when we got to this spot, we were like, oh, we're done, right? Here's our answers. Does anybody remember from pre-calc 1, what do you have to do when you square both sides of an equation? Anybody remember if you're solving an equation and you square both sides, do you have to do anything special? That's if you're taking the square root, you have to do a plus or minus. So, anybody remember that, like, if you're solving an equation and you square both sides, you have to check your answers because you could get things called extraneous roots. So you could get answers like algebraically here, we did nothing wrong, right? We get the algebraic answers of pi over 2, 3 pi over 2, and 0. But we actually have to check to make sure all of them work. So anytime you square both sides, you must check the answer, right? So if we solve by squaring both sides, we must check our answers. So we're going to check them back in the original equation. So if we look at x equals pi over 2, right, we're going to want to figure out is 1 minus the cosine of pi over 2, is that actually equal to the sine of pi over 2? So what's the cosine of pi over 2? 0, right? So we want to know is the square root of 1 minus 0, is that actually equal to what is the sine of pi over 2? Yeah, 1. So is the square root of 1 minus 0, does that actually equal 1? Okay, so let's be a little careful. So what square root of 1 minus 0 is 1 minus 0 is 1. So the square root of 1, is that equal to 1? Yeah, the square root of 1 is just 1, and so that is equal to 1. So pi over 2 works. Don't worry about it, everybody. Oops, says things like that sometimes. So pi over 2 works. So now we're going to check x equals 3 pi over 2. So same thing. Square root of 1 minus the cosine of 3 pi over 2. Is that equal to the sine of 3 pi over 2? Okay, so what's the cosine of 3 pi over 2? Okay, 0. So 1 minus 0. Is that equal to, what's the sine of 3 pi over 2? Yeah, negative 1. So now we want to know, is the square root of positive 1, is that equal to negative 1? No, right? So this doesn't work, which means 3 pi over 2 is not going to be one of our final answers. And then finally, we have to check x equals 0. So is the square root of 1 minus the cosine of 0, is that equal to the sine of 0? So the cosine of 0 is 1, right? So it's the cosine of 1 minus 1. And the sine of 0 is 0. So I want to know, is the square root of 0, is that actually equal to 0? Yeah. So our final answers are just x equals pi over 2 and 0. Questions? No. All right. Does anybody need me to wait a minute before I go to the next page? I know there's a lot of writing there. Okay, not a problem. Let me know when you're ready. Okay. Okay, so we're going to do one more example where we have to square both sides. So secant x plus 1 equals tangent x. So this problem is a little different, right? There's no square root, and so we know we have to square both sides because it's under my examples where we have to square both sides. But if I didn't tell you that, the thing is why would I square both sides? And so part of the reason I would square both sides is I have a function here, or I have an equation here, excuse me, secant x plus 1 equals tangent x. Secant x and tangent x are not the same. So the problem becomes like, I don't really know how to solve this. Like, I can't use an identity because my identities are kind of more involved. So I could square both sides. So I can make this secant x plus 1 squared equals tangent x squared. Now remember, when we have secant x plus 1 squared, that's really saying secant x plus 1 times secant x plus 1. And then that's equal to tangent squared x. And if I multiply this out, right, secant x times secant x would give me secant squared x. Then I'd have plus secant x plus another secant x plus 1, right? And all I did there was FOIL. So it's equal to tangent squared x. I knew, like, the squared part you're asking, how did I know I needed to square? Yeah, so I knew I needed to square because we have two trig functions. They're not related. They're not, like, I can't use a Pythagorean identity on it right away because there's nothing squared. And the secant and the tangent, I can't have both a secant and a tangent in my problem. So the thing is I know that I have the Pythagorean identity that says the tangent squared theta plus 1 equals secant squared theta. So I know that I could relate secant squared and tangent squared. So that's why I'm squaring both sides, to get some squares into my problem. Does that answer your question? Yep, yeah. So a good bet is if you have a problem and there's nothing you can do, I would try squaring both sides. Yep. No problem. So now if I collect up the like terms, right, I have secant squared x plus 2 secant x plus 1 equals tangent squared x. And if I look at these, the first thing is, so now I have secant squares, I have secants, and I have a tangent squared. But now the nice thing is I can rewrite my tangent squared in terms of secant squareds, right? So over here, tangent squared theta is going to be secant squared theta minus 1. So we're really going to have secant squared x plus 2 secant x plus 1 equals secant squared x minus 1. And now what I'm going to want to do is take everything and move it over to the left-hand side, right? So that I can get it into a point where maybe I need to factor it or see what's going on. So if I do that, I have secant squared x plus 2 secant x plus 1 minus secant squared x plus 1 equals 0. So questions on anything I've done so far? Okay, so my secant squared x's would cancel each other out. So we're left with 2 secant x plus 2 equals 0. And now I just have one trig function, so this is just like we were solving the other day, right? So I could subtract 2 from both sides, so 2 secant x equals negative 2. Divide both sides by 2. So the secant of x is equal to negative 1. Sometimes, right, so some people have no problem thinking about secants, and they would just know, oh, the secant x is equal to negative 1 when x is equal to pi. But some other people might have some issues. So remember, you can always convert it to cosines. So remember, secant is 1 over the cosine of x. So we're saying 1 over the cosine x is equal to negative 1. So we could flip that. So the cosine of x is equal to 1 over negative 1. Or we're looking for where the cosine of x is equal to negative 1. And then you get x equals pi the same way. Right, so you could go right from here, the secant of x, down here to x equals pi, or you could do all those middle steps. So remember, though, we squared both sides, so we're not done. We have to check our answer, right? So if we check our answer, we're looking at x equals pi. And again, you want to go back into the very original before you've squared it. So we want to know, well, is the secant of pi plus 1, is that equal to the tangent of pi? So the secant of pi, we said, is negative 1. So is negative 1 plus 1, is that equal to, so what's the tangent of pi? Remember, tangent is y over x, right? So it's 0 divided by negative 1, so it's going to be 0. So is negative 1 plus 1 equal to 0? Yeah. So this works, which is nice. So our answer here is just x equals pi. Sure. So remember, secant, so if you remember back from when we found sine, cosine, and tangent, right? So, and secant, so if you remember back stuff before the first test, right? We would write down, oh, here's what the sine of theta is, here's what the cosine of theta, here's what the tangent of theta is. And then remember, we would flip them over to get the sine pairs with the cosecant of theta, the cosine pairs with the secant of theta, and the tangent pairs with the cotangent of theta. So once we found sine, cosine, and tangent, we'd flip them to get the other three. So you can flip them back the other way. They flip both directions. So basically, if the secant of x is equal to negative 1, I could flip it. I could flip the negative 1 to figure out what the cosine is. So cosine would also be equal to negative 1. These steps in here are just that actually me writing down, flipping it, right? So secant is the same as 1 over the cosine of x. So that's still equal to negative 1. And then I flipped it. So if I flip this fraction, I get cosine x. And if I flip this, I get 1 over negative 1. Does that help? Good. Other questions before we do other problems? Need to put it. Today's the first day of the second 8-week semester, so I taught all morning long this semester, or the second 8 weeks. On Mondays I teach in the morning too, so we're getting to a point where my voice is like, ugh. Let's see. So if pi did not work, would it just be no solutions? Yeah. So if you plugged in pi, since pi is the only solution we got here, and it didn't work, then the answer would be no solutions. Yep, exactly. Other questions? Does anybody need me to wait to go to the next page? Okay, not a problem. I can do that. So let me know when you're ready. Because then we're going to move on. We're still going to be solving equations, but there's kind of one big overarching concept that we still have to do. No problem. Okay, so that's all the techniques really for solving equations. The thing is, the types of equations we have left to solve are, if you notice, all of these equations that we did before, our angle was always x or theta, but it was just a single thing. So now the question is, what if our angle isn't just x or theta? So what if we want to solve something like this? So find all solutions to 2 sine 3x plus 1 equals 0. So now the problem is, or not problem, but the difference is, instead of here just being an x, I have 3x. So what we're going to do is we're going to get a little crafty, actually. We are going to make a substitution. So we're going to solve the equation as if it was just a single x, and then we'll worry about taking care of the fact that it's more than an x at the end. Just like before, when you're trying to find all solutions, remember from last class, the problems where we found all the solutions are the ones we added that plus 2k pi. So just like before, we're going to have to add that plus 2k pi into these problems. So we're going to let theta be equal to 3x. And so rather than the original equation given, we're going to solve the equation 2 sine theta plus 1 equals 0. So we're going to go about doing that just like we did last class. So I would subtract 1 from both sides. So we have 2 sine theta equals negative 1. Divide both sides by 2. So the sine of theta equals minus 1/2. And then remember, in these ones where it was find all the solutions, we always had 2 sets of answers. So we found the places on the unit circle. So where on the unit circle is the sine of theta equal to minus 1/2? So 7 pi over 6, 11 pi over 6, plus 2k pi, plus 2k pi, right? So that's how we solved them last class. Questions about any of that? I'm not done with the problem yet, but anything I've done so far on the problem. Okay, so now that I solved, I know what theta is. Now we can plug back in. Remember, theta was representing our 3x. So I'm going to come up here. So this is saying 3x is equal to 7 pi over 6 plus 2k pi. Or 3x is equal to 11 pi over 6 plus 2k pi, right? Those are our two, so our two answers were theta equals 7 pi over 6 plus 2k pi, theta equals 11 pi over 6 plus 2k pi, and I'm just replacing the theta with 3x, since we made that substitution at the beginning. Oops, I see my pi didn't kind of come through there. So now, I need to solve for x, so what do I need to do to solve for x? Yeah, divide each of these pieces by 3. So we're going to divide this by 3, divide this by 3, divide this by 3. So x is going to be 7 pi over 18 plus 2k pi over 3. Alex might write this as 7 pi over 18 plus 2/3 k pi. Either way is correct. It's the same thing, right? And then this other one, again, divide by 3, divide by 3, divide by 3. So x is going to be 11 pi over 18 plus, again, 2/3 k pi. Questions? No. Should we try another one? Does anybody need me to wait to go to the next page? No. Okay, B. Cotangent of x minus pi over 2 plus square root of 3 equals 0. So again, you can have weird things, right? So it's okay, just whatever your weird thing is, that's what we're going to let be theta. So we're going to let theta be equal to x minus pi over 2. So we're going to have the cotangent of theta plus square root of 3 equals 0. Again, solve for this. So this is saying that the cotangent of theta is equal to minus root 3. Again, it's sometimes hard to think about what the values of the cotangent are, so it might be easier for you to think about the values of tangent. So if the cotangent is if the cotangent is minus root 3, the tangent is going to be that flipped over. So the tangent of theta is going to be minus 1 over root 3. Sure. So all I did so far, right, kind of to recap, why let people kind of catch up with me here. The first thing I did was I have the cotangent of a bunch of stuff that's not just an x. So since it's not just an x, I'm going to replace this with a theta. So whatever is inside here, I'm going to make theta. So theta is going to be x minus pi over 2. And then I just replaced it. So I used to have the cotangent of all this stuff, so now I have the cotangent of theta plus the square root of 3 equals 0. And then I just solved that for the cotangent. So I subtracted root 3 from both sides. So we have the cotangent of theta equals minus root 3. And then if the cotangent of theta is equal to minus root 3, the tangent of theta is equal to minus 1 over root 3, because they're just flip-flops of each other. Questions so far? All right. So when is the tangent of theta equal to minus 1 over root 3? One of the places is 11 pi over 6, and the other place is 5 pi over 6. So theta equals 11 pi over 6. Again, because these were solved to find all the solutions, we're going to add a 2k pi. Or theta is going to be equal to 5 pi over 6 plus 2k pi. Okay, so I add that 2k pi part because it's find all the solutions. And now, all I'm going to do is I'm going to replace theta with what we said it was, right? So up here we said theta was equal to x minus pi over 2. So this is saying x minus pi over 2 is equal to 11 pi over 6 plus 2k pi. or x minus pi over 2 is equal to 5 pi over 6 plus 2k pi. And now I just have to solve both of these for x. So to solve them for x, I'm going to add pi over 2 to both sides. So x is going to be pi over 2 plus 11 pi over 6 plus 2k pi. Or x is equal to pi over 2 plus 5 pi over 6 plus 2k pi. And I want to put together those pieces that don't have the k in them, right? So I want to add together pi over 2 and 11 pi over 6. So if we think about it, to add those, they're fractions, and to add two fractions, I have to have the same denominator. So I can make this 2 into a 6 by multiplying the bottom by 3. But if I multiply the bottom by 3, I also have to multiply the top by 3. So this one turns out to be x equals, so my denominator is going to be 6. I have 3 pi plus 11 pi, so it's going to be 14 pi. So 14 pi over 6 plus 2k pi. And I could reduce 14 over 6, right? So 2 goes into 14 7 times, 2 goes into 6 3 times. So we're really talking about 7 pi over 3 plus 2k pi. So that's one of the answers. Then we're going to do the same thing on the other side. So again, the common denominator would be times 3 times 3. So x is going to be equal to, so the bottom's going to be 6, so I have 3 pi plus 5 pi is 8 pi plus 2k pi. And then 2 goes into 8 4 times, 2 goes into 6 3 times. So x is going to be equal to 4 pi over 3 plus 2k pi. Questions? No. Does anybody need me to wait? So sure, tangent, so the tangent is sine over cosine, but if you change it to sine over cosine, that might not help you a ton. The thing that you want to, so that's why, so remember up in the quotient and reciprocal identities, there's a bunch of different identities. So remember that the tangent of theta is equal to sine theta over cosine theta, but the tangent of theta is also 1 over the cotangent of theta. Or another way of saying that is that the cotangent of theta is 1 over the tangent of theta. So that's why we flipped them before when we were finding, like if I just gave you, find all the 6 trig functions of pi over 3, we would find the sine, cosine, and tangent of pi over 3 and then flip them over to get the cosecant, the secant, and the cotangent. So that's all I'm using there on that part. Does that answer your question, Liana? Okay. Then Brendan, would we not put K, E, Z in our answer? K is in Z. So I'm just lazy. Mathematicians are lazy, and I should technically have where K is in Z. In Alex, they give you the pi K is in Z part automatically. If you on the test don't put the K is in Z part, I'm not going to mark you wrong. As long as you have the 7 pi over 3 plus 2k pi, I know you know what you're doing. Does that make sense? Other questions? So the last types of problems are still going to be these ones where the interval is where the angle isn't just an x, but this time we're going to have an interval. So solve on the interval 0 to 2 pi. Okay. And I'm going to add in my picture here of the unit circle, just because it's going to come in a little handy for us to use here. Okay. So A, the tangent of 2x equals minus root 3. So they've already solved it for the tangent part. But again, I have a 2x instead of just an x. So we're going to, just like we did before, we're going to let theta be equal to 2x. So since I don't have just an x, I'm basically going to force it to look kind of like the problems we did last time by letting theta be equal to 2x. So that turns my original problem into the tangent of theta equals minus root 3. When you have an interval, it requires a little bit of an extra step. So what this interval is really saying, right, is this interval is saying my original problem, that it's saying that x, my answers, are between 0 and 2 pi. Right? That's what that interval means. So when we write the interval 0 to 2 pi, we're talking about our answers that are sitting between 0 and 2 pi. I'm looking for 2x, right? So if I took this interval and I multiplied everything by 2, what that's saying is 0 is less than or equal to 2x less than 4 pi. So how many times around the unit circle is 4 pi? Okay, so remember, once around the unit circle, right, you start here at 0, you go all the way around one time, that brings you to 2 pi. So 4 pi means around the unit circle twice. So when we're looking for our answers, we're going to have to go around the unit circle twice, right? So whatever your interval is, that's going to change how many times around the unit circle you have to go. So we're looking for where the tangent of theta is equal to minus root 3. So does anybody remember where the tangent of theta is equal to minus root 3? So 5 pi over 3 is definitely one of them, right? So on this spoke here, so you go all the way around to here, right? So theta could be 5 pi over 3. Where else? Okay, theta could be 2 pi over 3, right? So theta could also have been here, right? And we just went this way. So that's if we went around one time around the unit circle, right? We have to go around a second time. So if you think about it, I go all the way around once, and then I stop there. So it's also going to happen at 2 pi over 3 plus 2 pi, as well as I could go all the way around once, all the way around the second time, and stop on this line again. So that's 5 pi over 3 plus 2 pi. So these first two answers are from the first time around this unit circle. And these second two answers are from the second time. And remember here, we just said this means we have to go around twice. If this had been a 6 pi, we would have had to go around 3 times. And then what we're going to do is we need to add what those values actually are, right? So theta is going to be 5 pi over 3, 2 pi over 3. If I add those other ones together, right, So if I make a common denominator, remember this is over 1, so times 3 times 3. So I'd have 2 pi plus 6 pi, so 8 pi over 3. Same thing over 1, so times 3 times 3. So I have 5 pi over 3 plus 6 pi over 3, so 11 pi over 3. So those are the answers from going around the unit circle 2 times. Remember, I need to get to x, right? So my original problem, theta was 2x. So this is saying 2x is equal to 5 pi over 3, 2 pi over 3, 8 pi over 3, 11 pi over 3. So if we divide everything by 2, x would end up being 5 pi over 6. In this second one, the 2's would actually end up canceling. We'd just get pi over 3. The next one, we could cancel. We'd get 4 pi over 3, and then 11 pi over 6. So you end up with these 4 answers. Questions? So some people are asking questions about the test. So let's talk about the test for a couple minutes that we have left here. And I can put up a video too that has some more of these examples where I did these problems. So I'll put that up next to where I put up the lecture notes. I'll also put up a link to more of these examples. So in terms of tests, right? So the second test is not this Wednesday, but the following Wednesday, so the 24th. After this, there is one more test, which is actually not an in-class test, right? So it's a take-home test. So we're not going to spend class time taking the test. And then there's the final exam. So there's basically, after this test, there's like 2 more test things. So does everybody have this written down? Can I share my Canvas screen so that I can show you where stuff on Canvas is? Or where stuff on Canvas is? Does anybody need me to, does anybody need me to wait to go off of this screen? No? Okay. Stop sharing that and let me reshare. Pull up our course before I share my screen here. Okay, so if I share my screen here. Okay, so if you go to our course, right, and oh, thanks, yeah, this is my pie sweater, right? Yesterday was Pie Day. So if you go down to test reviews, right, and you click on the test review, you will see that I put there, click here for test 2 information, and extra practice sheets. So I put up a lot of stuff for you guys to practice, right? As I said at the beginning of the class, if you came in, under the second one, under solutions, there's no solution. Here where it says solutions to extra trig inverse practice, nothing comes up. I don't know what happened. Under, let me see. So you're saying the solutions to practice problems doesn't show you anything? Okay. I was going to say, I thought I tested them all. No problem. I want to make sure they're there. Okay. So here under this, right? So I have the information. So the test will be similar to how we did before, right? It'll be under, like, you're on Zoom, and like then when you're done, you take pictures, you upload it. So if we look at this, what to know for the test and the practice problems, it doesn't want to let me preview it. So did it change the screens? Can you guys see the like document that says what you should know? Like the test 2 review. Is that what you guys can see right this second? Okay, perfect. So if you look at it, right, so there's really only 3 things you have to be able to do on the test, right? Be able to find exact values of inverse trig functions, be able to use trig identities, and be able to find values of, or be able to solve trig equations, right? So you'll notice I kind of broke them up. So here's what those inverse trig function problems will look like. Then you have these solving problems. Now you'll notice, right, there's not many problems where I tweaked with the angle, right? Like in here, there's 1. On the test, there might be 1 or 2. And then there's some identity problems, right? So the identity problems are going to be things kind of like this. They're just going to be more applying the identities. I will give you, in the test document, I will give you that identity sheet. You can also, if you want to print off the identity sheet, it's under the handouts. So if you want to print it off before the test, you can do that. And then also the 2 biggest parts of the test, right? I think I kind of said this before, but the 2 biggest parts of the test are the inverse trig part and the solving equations part. So I gave you even more practice. So here are even more practice problems on the inverse trig. Here are even more practice problems on the trig equations part. And so what we're going to do in class on, so remember, no class on Wednesday, but on Monday, next Monday, so a week from today, the next time we meet, that will just be for you for review. So if you have any questions on any of this stuff, you want me to do any other kinds of problems, you want to see more of a type of problem, that is what Monday is for. Anybody have any questions? There's no class this Wednesday. I have a doctor's appointment that I could not change. That's been set up for a while. No, you're not going to have to prove any kind of identities on the test. Yeah. Other questions? Yep, I can definitely do that. Anything else? Yeah, so I won't be in office hours on Wednesday, but I'll be in office hours the rest of the week. So today and Tuesday and Thursday, just not on Wednesday.